I was trying to answer question A6. That A6, what we're given here is the constant speed of 1 meters per second, meaning the initial and the final is just the same. The mass of the elevator is 1000 kg. We are also given gravity. We're told to find the power. And I started driving. That power is equal to work done divided by time. But work done, we are not given, time, we are not given. So what is work done? So work done is equal to force times distance. So work done is equal to force times the distance. So this force times distance is what is being divided by time. Okay, now what is force? Force is equal to mass times acceleration. So mass times acceleration is ma multiplied by d, mass times acceleration here, then we divide by time. What else do we know? We know that acceleration is equal to speed over time, which we can say as velocity time minus 1. And therefore, basing on that, we are going to say that the acceleration that we have there is acceleration due to gravity. So, so this is what we know that this is what we have as the acceleration. But not only that, what about speed? Speed is equal to distance, speed is equal to distance over time. Speed is equal to distance over time. So here where we have got speed over time, we are going to put, here we have got distance over time, we are going to put speed. And therefore, this is mass times the acceleration, which is due to gravity, and then times the velocity. So this is how power has been reduced to. Allow me to go through again. We're saying power is equal to work done times distance, or work done over time. And what about work done? It's force times distance over time. But what about force? Force is equal to mass times acceleration. So mass times acceleration is what we have here, representing the force, times distance over time. But speed is equal to distance over time. So here we've got distance over time here. We are going to put the velocity. So meaning this is a formula that we are going to use because we have the mass, we have the acceleration due to gravity, we also have the constant velocity. So now what do we have? Our mass, the mass of the elevator, we're told that is 1000. It's 1000 multiplied by the acceleration due to gravity, it's 10 multiplied by the velocity that we have is a constant velocity. And therefore, when we get this information here, and then we multiply, we'll find that our answer will be 10,000 watts as our power. So meaning the answer here is C. So this question was a little bit involving because the parameters that we had were not exact, meaning you have to do a little bit of derivation until you find the answer. And this is how the answer is found. Question number 7. Question number 7 is saying, zoom out. Okay, so question number 7 is here where it's saying that the following diagram shows a pulley. We have on the pulley here, we have the effort, the force being dragged this way, and we have the F here, which is the load, the weight downward. This is what we have. I'm saying that if the man using the pulley pulls on the rope at point E here with a downward force, and the rope moves 16 meters downward, how high will the load F be raised? How high will this load be raised? So what are they talking about? What they're talking about here is the velocity ratio, where we say that velocity ratio VR is equal to the velocity ratio is equal to, so the velocity ratio here is a distance moved by the effort, because the effort moves a longer distance over the distance moved by the load. But from a pulley system here, we can find the velocity ratio by just counting the number of ropes. So let's count them. We have 1 here, we have 2 here, 3 here, as well as 4 that are connected to the wheels. So meaning our velocity ratio here is 4 equal to the distance moved by the effort. This is a distance we are told that the rope moves a distance of 16 meters. Then what will be our distance moved by the load? So here when you cross multiply, you are going to have 4D. You're going to have 4 distance moved by the load is equal to 1 times 16 gives us 16. And it's from this effect that when you divide by 4, you also divide by 4 here, you'll find that equally, even the distance moved by the load will still be 4 meters. So here you have to use the formula for the velocity ratio. And then once you use that formula for the velocity ratio, you find the parameters given, you substitute them, and then you'll be able to solve for the one that is not given. So the distance moved by the load was also 4 meters. A8 rather. A8 saying, what is the main reason why food is cooked faster in a pressure cooker than in an ordinary pot? So we go to what we understand that the higher you go, the cooler it becomes. So you see, if you have a mountain here, at this point here, which is highly elevated, here the room temperature is low. The temperature is low. The higher you go, the cooler it becomes. And what do you know about low temperature? According to thermodynamics law, when the temperature is low, we expect the volume also to be low temperature. We expect the low temperature. We expect the volume also to be low, thereby pressure how am I failing to write? Let me try to change sound. Okay, so low temperature, we expect the volume to be low, and then the smaller volume, the pressure is high. The pressure is high because the space is small, then the pressure is high. Now, what happens in the pressure cooker here? What happens in the pressure cooker here is that inside of the pressure cooker, the pressure is very low inside of the pressure cooker. And what causes that? It is because inside of the pressure cooker, the temperature actually is very high. So meaning the temperature at which the water boils inside of the pressure cooker is higher than the boiling point of water in an ordinary pot. So in a moment where I've got two substances that are in two different environments, this environment is having high temperature. This other environment is having low temperature. The environment with high temperature, we expect the cooking to be done faster. So the reason as to why inside of the pressure cooker, the food, even beans, cooks faster than in an ordinary pot is because the boiling point of water is already raised above the ordinary temperature. So meaning the beans or the food that is in there is being kept at a very high temperature. As a result, the cooking is also faster. Just like when you have an egg or you have meat, then you put these two relish types of relish in different pots with different temperatures. We expect the one which is at high temperature to get cooked faster. So this is why C is the answer. N9, so here you say this is the answer. N9, in a thermal flask, a vacuum space reduces heat transfer. So we know that there are only three heat types of methods by which heat is transferred. So we have conduction, this one is through solids. Okay, so because in a vacuum there is no solid, conduction is prevented or is reduced. What else? Convection. So convection is a transfer of heat through fluids. Now these fluids are liquids as well as gases. Liquids as well as gases. So because of the fact that inside of a vacuum there are no fluids, also convection is reduced or maybe even prevented. But now the other one is called radiation. Radiation is a transfer of heat in form of electromagnetic radiations or in form of electromagnetic waves. And these waves can travel even, they don't even need a medium. So meaning in a vacuum, these waves can travel. So because of that, we are saying that a vacuum can only reduce heat transfer by these two methods, which is conduction and the convection. The answer here is B. 18, halfway the section A. Which feature in a liquid in glass thermometer increases its sensitivity? Now here there are two things that we are talking about. There are these words that sound a little bit similar. They are similar, but they are not exact the same. Sensitivity, something which is sensitive. Sensitivity. Sensitivity is the ability to detect. Yeah, that's sensitivity. The ability to detect, maybe in biology you can say the ability to detect the stimulus. Just to detect, it means you are very sensitive. But when you detect, are you able to respond? Are you able to provide an action to the detection? Let's say you're seated on a nail. Uliingiza chepa mspikiri pa. Then someone from behind says, taps on your shoulder. Anyway, are you seeing where you're seated? You're seated on your nail. Then you go like, yes, I felt it. You felt that you're seated on the nail. Why didn't you move? Meaning now there, you are not good at providing a quick response. So sensitivity and quick response, they are somehow connected, but are not the same. Someone may be sensitive. Someone is calling you, Trisha. Trisha, they are calling you ahead. But you heard, why didn't you provide a reaction to that? Meaning you are sensitive and you are not very good at providing a quick response. And because of that, there should be no one who is good at providing a response before he detects. You can't start running before, you can't start crying before you are beaten. You are good at providing a quick response before you even detect a pain. So being sensitive, being good at being able to detect, this can only happen when the bulb of a thermometer is made with a thin wall. The bulb of a thermometer made of a thin wall, as well as having a narrow capillary. A narrow capillary will enable the thermometer to provide a very, no, this is sensitivity. This is quick response now. I'm trying to, yeah. So being sensitive is having a large bulb, as well as a large bulb, yes, and then being able to respond so quickly. It's yeah, a thin wall around the bulb. Let me just show what I mean. If this is the thermometer, and then at the very tip of this thermometer, this is our thermometer. I'm just drawing. At the tip of this thermometer, if this wall is very thick, you'll find that even when heat comes in here, remember mercury is inside here, because this thing is very thick, it will be very difficult for heat to be transferred into the inside of mercury, for the mercury to start moving the side. So that's why we're saying that this wall must be very thin. Secondly, now because they did not talk about the sensitivity, I'm sure maybe that's the angle they were trying to look at. So, but basically, where you see the narrow capillary, it's for the quick response. But it is because something which is sensitive, we should also be able to provide a quick response. That's how we can settle for this, because the thin wall is not there. But if the thin wall of the bulb was there, meaning that could have been our best answer. Question A11. Which of the following diagrams show the correct path of the ray of light passing through a glass prism? And a glass prism, we understand very well that when light is moving from a denser into a less denser, maybe let me put up those points. Dense, the font is too big. Let me try to reduce it a little bit. So you're saying denser to less denser. The ray of light bends towards the normal. And if the ray of light is moving from from a less denser to a denser medium, it bends away from the normal. So this is what we are going to follow to answer this question. And we also have to understand that at the point of intersection between the media, at the boundary between between the two different media, where the ray of light is striking, there's a normal that is drawn, and that normal must be at 90 degrees. So let's go through this A that we have here. Unfortunately, this cannot move, so I have to use a different one. So this ray that we have here, if we are to, let me even use this smaller one. If we are to draw a normal, this normal can be drawn at 90 degrees. It's drawn in hidden details, but I may not draw it rightly in hidden details. So allow me to draw it here. And right from here, we are saying if this ray of light is moving from air here into the glass block, for as long as it is moving from a less denser into a media, we expect it to bend towards the normal, and it must be on the other side of the normal. But we can see that this bending was away from the normal, and not only that, this ray of light has to be on the other side, then here it bends towards the normal. So because this is just more or less like bouncing from the normal, bouncing back from the normal, this only happens when the two media A and media B, are of the same density. Now, because air and the ray of light and the glass prism are at different density, this thing can never happen. We expect the ray of light to do a little bit of bending. So this is wrong. This is grade 9 science. What about this other one that we have on D? If we are to provide the normal here, it's more or less like the one we had here at number A, answer A, which is also wrong. Now let's see the one we have here. At 90 degrees here, we can even see that if this ray of light was allowed to go through, this is how it was supposed to move. But what really happens to this ray of light is that it had to bend a little bit towards the normal because the ray of light was moving from a less denser into a denser medium, which is point number 1. What about at point number 2? At point number 2 here, if we are to establish the normal, like I said, it must be drawn in hidden details and at 90 degrees. But because I'm doing some freehand, it may be a little bit hard. And you see, if this ray of light was to be allowed to go straight, this is how it could have moved. But look at how it moved. It moved away from the normal because this ray was emerging. And that's how we are saying that this is how the ray of light is supposed to move across the medium. The medium from a less denser into a denser into a less denser. And here the answer was B. So you can answer this question better if you're in an exam with a protractor, you draw the nominal ray at 90 degrees, blah, blah, blah. You do a little bit of a follow-up, then you will understand that B was the perfect answer. A12. So A12 here, the following diagram shows a transversal wave. How many complete waves are shown in the diagram? So a wave starts from here, according to the information that we're given. It starts from here, going down, going up. This is a single half, then going up again. Getting back here is as good as starting from 0. So this is one wave. The second wave is here. We start from here, we go up to here. This is another wave. Then the third wave is starting from here, we go up here. So this is what we have. So here we only have 3 complete waves. This was the simplest of them all. The simplest of them all. A13. The following diagram shows 2 forms of waves. Not types, but forms, 2 waveforms. So we have the first one where we have the displacement on the x-axis. We also have the time. We have the displacement here. We also have the time. So these 2 waves are different in some ways. How different are they? We can see that the amplitude here is 4. The amplitude here is 3. But the wavelength may not be the same, may be the same, we don't know. But one thing we know is that the time taken for a complete wave, 0.1, even for this one, 0.1. So the period is the same, the frequency is the same, the wavelength, we are not too sure. So, which property of sound waves is different in the 2 forms? So we are saying for as long as the time taken for a complete wave to be made by a particle, then even the frequency will be, the period is the same and the frequency will be the same. Therefore, when the amplitude is different, what is different here is the loudness. How? When you have JBL, JBL, these guys can make good machines with buzz. When it is playing, there's so much loudness around the place and it's buzzy, but you'll find that that buzz doesn't go very far. Male voices are just loud around here, but they don't go very far. But should you allow a woman to sing in an alto voice, especially in the evening, so you hear the voice going up far, but around the singing there, it might not even be that loud, but that distance will go very far. So when the amplitude is different, what is affected is the loudness. If the wavelength was different, what could have been affected would have been the pitch. So what affects how loud the sound is? The vocal, the amplitude. And that's the reason as to why when you're playing music in the car or maybe anywhere in the home theater, when you hold your hand on the speaker, you'll find that the buzz reduces because the pushing of the particles to produce the maximum amplitude is not there. So find that even sound reduces. But the moment you remove your hand from the speaker, you'll find that it becomes louder because the vibration or movement of particles on the diaphragm as it produces sound has been enhanced. So here, your key component was looking at the maximum displacement of the particle. Because these are different, we expect the loudness of sound also to be different. Okay, 6 minutes. Let's see how far we can go. Which statement is not true about a magnet? Meaning, because we have 4 answers, so meaning 3 of them are true, but 1 is not true. So the first one is we're saying a magnet attracts all magnetic material near it. This is very true. For as long as it's a magnetic material, it will be attracted. A B made up of a magnet is made from a magnetic material. It's very true. How can you how can you cook nishima from something that people don't eat? A magnet is made from a magnetic material. When the magnet is suspended, when it comes to rest, it lies in a north-south direction. And that is very true. But for as long as we have a magnet, it should have different ends. North here as well as south here. There is no magnet that can have the same ends. Okay, then we go to, remember they are saying always. They are saying always. They are saying always. It is not always that a magnet will be made up of the north and south always. There are some special magnets, this is maybe your homework, which are made up of same polarity. And these magnets have got special names and they also have a special use. So that's your homework. Go find out. So magnets, it's not always, the key component here was always, it is not always. And this only happens that when the method we are using for making magnet, which is maybe double stroking like this, you have south pole here and you also have south pole. And this, the stroking is being done in this way. You'll find that if this happens, then this would be the south pole and this would be the south pole. Meaning here, that's where we're supposed to have the north pole induced terminal. It depends on how this magnet was made. So it's not always, therefore C qualifies to be the answer. 1-5, A15, A15. Which diagram correctly here, the key component here is correctly, this is now static electricity, represents results obtained when a charged gold leaf electroscope is brought closer to the charged metal rod using the shown, okay, which diagram correctly represents results, okay, represents results obtained when a charged rod, a gold leaf electroscope is brought closer to a charged metal rod. Okay, so here, one thing that I want to guide you is that we cannot have the positive here. According to the fundamental first law of electrostatic, the repulsion can only happen when they are opposite charges. If they are the same charges, we expect some form of repulsion. This one pushes this one pushes this side. So this can't happen. This also can't happen. This can't happen. Therefore, without even wasting much of the time, fundamental first law of electrostatic guides us, meaning we expect the negative charges to be pushed on the gold leaf down here. This is what happens. We go to 2 minutes. A16 here says, the following diagram shows a CRO cathode ray oscilloscope with a bright spot formed on an AC generator. So on an AC generator, we've got two axes that we can even see from here. There's this one here, there's this one here, which is an x-axis. X-axis is actually, we follow the wavelength. We follow the wavelength, and the wavelength helps us to detect the time interval, and the deflection is on the X plate. Okay, then we also have this y-axis. This y-axis represents the amplitude, and the amplitude actually we use it to calculate the voltage peak on the grid. But we can see that this spot actually was just here. The spot was just supposed to be here. But this spot produced a deflection here, also produced a deflection here, though we had a major deflection in this axis. But both of them are there. So as a result, any of these two can be the answer, unless the question talked about the major deflection which was done. But in both axes, there's an observation which is made. So A and B still the answer, because there was an observation on both ends. Then A17 is talking about the electricity, current electricity. So I don't start the diagram. So we have the first resistance with the resistor of 4 ohms. Second one, we don't know. This one, we don't know, but both these two are in parallel, and then these two parallel are in series with that one. So calculate the value of X. Find this resistance, which is here. If the current here was 2.5 amps, and then the voltage was